arrived yesterday morning and learned more about the audience, I thought maybe I should have spoken about perceptron or block model, but Lenka opened the Pandora box of deep learning, so I'll continue on that. The topic is learning sparse Boolean function with neural networks. So there are Boolean functions. And the goal is to tell you about this measure, deep complexity, that showed up in line of work. That seems to be something that I've not seen before and seems have quite an important role in this context. It would be nice to see if it appears in other contexts. So it's joint work with two students, Henrik Boysch at Sarah, who's at MIT, and Theo Niziakiewicz, who's at Stanford, the student of Andrea Montanari. Just left yesterday Switzerland to go back to the US. They were both PhD and really outstanding students. So I will set up the model. It's related to what Lenka talked about this morning, a slightly different notation. What is the setting? So as I said, we focus on Boolean functions. Dimension D for the input, plus minus 1. Take value in some alphabet subset of the real line. Could be plus minus 1 also. That would be two classes like cats and dogs. Or it could be the entire real line. And then it's more regression. Okay, so that's the target function. We don't know it. It's unknown. We'd like to reconstruct this. What we know is either we are given sometimes a class of function. So this is a subset of all possible functions. And often, I will write, this is, I will say, can we learn a specific function f that I will write? Of course, that doesn't make sense to, if we know what f is, there's no problem. But because we will use a model that has a lot of invariants, like the model, for example, is permutation invariant, then writing that specific f and learning it means that you can learn the entire orbit of all the other functions. So what I mean by this is often this class of function that we know is the orbits of a specific function f over some group. For instance, so what is this? These are all the f pi such that pi is in the group. And this thing here, f pi of x, is simply f pi x. So for example, the most common one would be permutation. If I say that we can learn this function, what I mean is that you take all degree 7 monomials, and this class of all degree 7 monomials, is it learnable or not? Okay, so now the observation, what are we given to try to estimate this f? The data we get to see, I'll assume that it's IID. It's classically assumed in the learning theory from a distribution, which in this case I will fix it to be uniform over the cube. Often in learning theory you may have some hidden distribution and you want to succeed with worst case guarantee on the distribution. Here I will simply set it to be uniform. And what you get to see is the value on this specific sample. You get to see the value through the target function that you try to estimate. And this entire collection of point sample with their value through the target function is the sampling set that I call S superscript m. So m is the number of samples. So it's an important parameter. Often we have complexity that depend on how many samples we will need in order to succeed. So I have to tell you what is the succeeding task. So the next thing is we need a learning algorithm What is this? This is simply a map that takes such a sampling set, I'll call it f hat, and outputs a function, f hat, that depends on this sampling set of dimension m. So this is a function, again, that is defined on the same domain as the function that we try to estimate. And the objective, so we talk about successful learning. We say we have learned, or if the following happens, so we get this estimator f hat that only depends on the training set that saw m examples. And now we want to generalize, so at the high level we want this guy to be close to f, but in what sense? There are different notions. Let's start with the case where y is plus minus 1, it's discrete. So then you would hope that if you look at a new point, I'll call it m plus 1 to stress that all the xi's are IID, so this is a new fresh IID sample. This is not the true value, so you don't get the right value on this point, m plus 1. And you ask the probability of this when you sample this new point x m plus 1 to be, so there are a few variants. So okay, you will say this is a small, less than epsilon, but there's still randomness in here, and there may be randomness in the map as f hat. So you can put the external randomness of the algorithm here. And either you do also an expected value of this over the randomness of SM, or often people say with the probability 1 minus delta on SM, you want this to happen. With probability at least 1 minus delta. Okay, so with sufficiently high probability on the sampling of your training set, you want to predict incorrectly with a bounded probability. And this delta could also be just sometimes you can think of it that you fix it to 1 over 10 and you get rid of one parameter. Now this is for if you have Boolean output. If you don't have Boolean output, then you will take a loss to measure the distortion between what you predict and the truth. So this is simply the expectation of the identity, the indicator function. More generally, what you can have here is the loss between f hat and f, and you do the expectation over your new point. And often I will call this quantity calligraphic L between f hat and f. This is still on SM. And the classical example that we use is the L2 loss. So this would be simply the gap between f hat minus f squared. For real valued function. Okay, so any questions on the setting? Okay, so now we will mostly focus on methods, algorithms that have a bounded complexity. So there's two sources to measure the complexity. The first one is on M. So we want M to be at least polynomial in D, where D is the input dimension. So that's the sampling complexity has to be polynomial in D, and we hope to control it, see how it scales depending on parameters of the problem. And the second is the time complexity. We also hope it's to be polynomial. Once you, yes?
You mean time to compute your f hat? Or?
Yeah, exactly. So f hat will access maybe polynomial number of samples, but if you do something very complex from it, okay, so the big question is, and I'll ask it first generically, but of course we will narrow down, is what class of function can we learn efficiently? So in polynomial time at least, and how do we control these different complexities here depending on the properties of the function, etc. So of course answering this depends on what is the algorithmic framework that you use. And I'll do a cartoon now to represent the possible algorithmic framework that we will discuss. There's this axis here. This is a cartoon, okay. Here, this is the algorithmic class complexity. I'll put two extremes. The first one is here. This is just you restrict yourself to f hat that are linear functions of the input. That's very simplified. So here, it's the sum of some weights times the xi's. Linear. Obviously, this is too restrictive. It's not expressive enough. If the function is not linear, you will have errors. The next natural thing to do, perhaps, is, well, before I grow this, the other extreme here is so this is linear. The other extreme is completely free algorithm. By this, I mean you collect your samples and you do whatever you want with it. We still ask the complexity scaling, but you have no restrictions on how you manipulate those samples. And if we go back to applications, the way I think people have tackled this problem for long is that they worked on a class of models that essentially correspond to training parametric models. And in particular, of interest is these neural net models. This is a neural net. And when I say training in this talk, it will always be using gradient descent algorithm, SGD. But before they got into the period of deep learning, the approach classically was to deviate from the naive linear method. So when would the linear method work? Well, if you go back to Y is binary, if your set is linearly separable, then of course you can find a good linear estimator. And this restricts yourself to very few cases. What you can hope to do and to go beyond this simple linear estimator is to come up with a feature map. So I'm going to put here a P instead of a D. And now you are allowed to use a choice of function, phi1 to phi p, that have to be data independent. Let's assume this is the class, and that will be called kernels. So in a sense, you decide to remap your input x into a new space of features that you believe are good, useful to predict. And then you again train a linear model on this feature space. This you fix ahead of time, but the training of this W will depend on your sampling set. So like the classical example is, if your data look like this, you have a bunch of minus and a bunch of plus around it. This is not linearly separable, but if you lift this into not dimension 2, but dimension 3 with a Gaussian-like kernel, so you put the minus here and the plus, they become at a higher component on the z-axis, then this becomes linearly separable by a plane. So once you lift to a better feature map, then linear models are much more expressive. And back in the application, the feature map was in the whole industry that's in computer vision, where people looked into, okay, we should look into short angles, contrast, specific features, etc. Okay, and then in this more recent trend of deep learning, the approach has been to say, okay, let's forget about handcrafting the features ourselves. Let's go back to models that are a bit more black box. So I'll define now two models, here and here. They all in this orange bubble, they all correspond to the following. You take your input x, and as Lenka mentioned in her talk, you apply some matrix W1. And then you apply a non-linearity that you choose, sigma pointwise to this vector. This is a vector, this is a matrix, that's again pointwise activation function that is nonlinear, and then you iterate this. New matrix, and let's say the same activation, and so on and so forth. So now the difference with before is that you don't do anything to preprocess X. This is directly hit by a matrix W that is going to be a parameter, a set of parameters, and then you may choose this function to be, for example, the positive part, or a sigmoid, or another function of your choice, and you hope that this composition is actually going to be a good parametric model to learn your function class. So this extreme here, that I'm going to call 2nn, corresponds to two-layer neural network with a choice of parameterization that is like this. So we'll denote capital N the number of hidden neurons. Typically, this is coming from notation from Andreas' paper. This second matrix, which is a vector in this case, so the dimensions are a matrix, and then this matrix has to go back to one dimension, so it's a vector. So A is going to be a vector, and then the sigma of Wi inner product X. This is exactly this model when you have W1 and W2 if you wish, but this becomes A. And this becomes just W. And these Wi's are really, so this is W1. If there's n neuron from here to here, this is 1 to D, and this is W1. And this is W2, etc. Now, what is the magnitude of this random variable? Initialization, you initialize them IID. How? This is going to be just on a bounded compact support, so with two constants. Doesn't need any scaling. This one needs to scale with D because we will do asymptotic analysis in D growing, and N actually will grow either very slow or not grow. And this will be the normalization. The Wi's will be IID, either Gaussian with 0 mean and 1 over D the identity, or uniform on plus minus 1 over D. That's the choice of initialization. And then here you normalize by N. Okay. I won't discuss further at this point why we like this parameterization, but in short, I think after a couple of 3 years, it's the one that showed most rich dynamics and expressivity. So I'll come back to it when I state the results. That's what I call 2nn. Okay, so 2nn is 2 layers in this choice.
So you optimize over A and W?
Yes, train both. Now the other extreme, which is closest to the free world, is free NN. Free NN is what? Is you choose those W's as you want, and the sigma as you want. No restriction on their structure, on the magnitude of the IID variance, nothing. You have complete freedom on choosing these parameters. So when I started working into this topic, most people were growing from here. And so I said, okay, I'm already 2 years late to understand what's going on here. But there was not clear understanding of what you could do in the free world. Like if you have choice, you're still forced to use gradient descent. So that's a quite strong restriction. So gradient descent means what? Means that your parameter theta t, so it's the union of these W's and A's, is going to be, so the next one is going to be theta t minus some learning rates, and then the gradient of the loss, that's where you are at time t, with a new sample xt compared to the true f of xt. So that's the true target. This is where you are. You take a gradient of some of the loss function that you use, and you subtract this. So this is SGD when you do with a single sample at a time. And so this is a much more restrictive class of algorithm compared to free algorithm, because you are forced to use a parametric model and do these linear corrections, additive correction to your parameters. But because you have so much freedom in the neural net class, you can still do quite a lot of hacks. And so in fact, this is what we showed with student Senden in, I think the first paper was 20 and the full paper is now. And what we show is that there's no gap between those two worlds. So there's no gap here, meaning we can emulate any free algorithm with neural networks using GD. Okay, so this is actually more of a, we were more disappointed than happy with its results. We were hoping that even in the free world, neural nets with GD may have a gap to pack. Sometimes I call this pack. But it doesn't. You can do anything you want Of course, the neural net that we construct to emulate any algorithms are completely unorthodox and very far from what is done in practice. So it was just a theory result, but it still tells you that if you can play with these parameters freely, you can go pretty far. Okay, but the real question that really connects more to practical applications is that you stay more in here. You like to use neural nets that have some regularity, because that's the power of deep learning, is that you don't encode too much in the architecture, you do something fairly black box, and so the regular networks that typically have these IIDness at initialization, fully connected connections where you don't have to encode too much. Okay, so that is the setting of the talk for today. Yes?
Can you explain what free neural networks mean?
Free neural network means the following. You build a class of functions that will correspond to iterating matrices of your choice with one nonlinearity of your choice. And you decide
Two layers or any number?
Any number of layers, any width, as long as the number of parameters is polynomial in the input dimension. Yeah. Okay, so this is what I'm not going to talk about. I'll tell you about results about what happened in this regular world. Where am I? Yes?
Then what do you mean by free algo?
So free algo is that you don't even have to use a parametric model with GD. You can just take samples, polynomial number of samples, and you do whatever you want in polytime with them. You don't have to be forced to use GD on a parametric model. And free neural net is the closest to that when you're forced to use the GD training on a neural net. And these two are actually the same.
You had subtlety whether you can train this with SGD or GD, is that correct? And
Yeah, that's true.
So which one is more powerful?
Yeah, so there was one interesting thing that came up here. It was that we could only get no gap to the free world if we were doing a stochastic gradient descent, where you take one or some, it could be more than one, but a reasonable number of samples. If you end up doing a population gradient descent, where you take the entire population, which in nice, well-behaved convex setting is better, here it hurts you, and then there was a gap between those two, which is that if you do full gradient descent, you're not universal. But I could go on discussing why this is not clear what this tells, but it's a bit on the side. Okay, so just 2 words on the free world. So maybe the first thing to say that when you are in the completely free algorithmic world, what we know, for example, is that if the class is finite, so when H, so let's just talk about the free algo a little bit. If H is finite, for example, the binary classification, then you can always get this epsilon delta learning as long as this number of samples is scaling like 1 over epsilon log the size of the class divided by delta. These are the first results you see in learning theory, and they're essentially union bound results that tell you that if you use as an algorithm the rule that matches all your examples, so you try to find an interpolator, and you output that as your answer, the probability that you have bad functions that are correct interpolator but don't have this epsilon prediction on unseen data will actually be vanishing as long as you have enough samples. That's the first statistical learning theory result. But that doesn't mean that you can learn in polytime. So even in the free world, if you want to learn in polytime, you still have to be careful. And for instance, if you look at the case of parity function, so it's just a product of the subset xi. Then, sometimes also there's confusion here that you can learn in polytime. This is a good case. You cannot do it if you have noise on top, but if you are the noiseless case, that you can learn in polytime. And the different ways to do it, you can either, for example, estimate, that this thing, if you if you know that you have a parity function and you know the size is k, for example, this is given to you, this is the family f, then if you know that this thing is going to be 1 if and only if these two sets are the same, so we can simply, by Chernoff, use a number of sample that is going to be 1 over, so again, log 1 over epsilon and 1 over delta and epsilon. And you will get basically that if this is small enough, so this is growing enough, you will be able to separate these two quantities, the 1 or the 0, by sampling and replacing. So let me write it like that. If you approximate this by the summation of this, by Chernoff-Hoeffding, that this will be away from half plus or minus epsilon. Let's say that if you take s, that it is equal to t, then the probability that this is away by, let's call this constant, this would be exponential in m by a constant that depends on this parameter. And therefore, if the number of elements that you have is cardinality of f, you just need the number of samples to be logarithmic in the size to actually separate all the possible cases. So this is perfectly learnable in a, even if this is exponential, like here, if k is n d by 2, this is exponential in d, but because you only need log of this would be polynomial. Okay? So it would be logarithmic in d. So it's like something you can do. There's no problem with that. Okay, then there are other classes that you can still learn because you are finitely with polynomial number of samples, but that you cannot learn in polytime. And this is, for example, the 3-term DNF. So this led people to look for the line of work in TCS, learning theory, with works by Mansour and Goldreich-Levin. I realized that a nice way to control the complexity of learning, the time complexity, is to actually look at the Fourier transform of the function f. And if it's enough concentrated, if you know that, so what is the Fourier transform? You can write any function f as a summation of the inner product of f and these basis elements that I defined just above over all s in D. Okay, so this is the transformation. You just simply, this is a function that depends on the xi. Xi square is 1, so you can always write it as the multivariate polynomial in the xi's. This is simply collecting the monomials as the basis elements. So people have realized that, I will use this notation for the coefficient, f subscript s. If the Fourier transform is concentrated, if it's localized on a few set of parameters of Fourier coefficients, then you can actually, and if you know who these coefficients are, then you can again learn efficiently by this kind of procedure, by just estimating those coefficients. And this led to this line of work about low degree learning or sparse learning. There's a couple of variants. There are some subtlety if you don't know. So in low degree, the advantage is that if the function is low degree, this is one way to tell you who are those important Fourier coefficients that you have to check. If you're sparse and you don't know, then there's the Goldreich-Levin that tells you that you can still do it, but you need adaptive queries. So anyway, the conclusion I want to mention about the free algorithmic world is that sparsity came up a lot in the Fourier basis to do efficiency. But in a sense, it's completely agnostic to which Fourier element you have. For example, if you can have the highest degree monomials or the d by 2, as long as you pick a finite collection of Fourier coefficients, it's the same difficulty. But clearly, some of these functions are much more complex to learn than others, or not to learn, but let's say, if you care about noise sensitivity, this function has a much higher noise sensitivity if the size here is larger than if it's a linear function, if this is a singleton. Right? The x1 is much less noise sensitive than x1, x2, x3, etc. So where does this factor in, and you know, what is there a finer picture? It doesn't show up for the free world, but as we will see, it will show up for the regular neural networks. Okay, so now I want to tell you two results. So the first one is that maybe I put it like that. I'll mention to you three functions. So let's look at three examples of function. The first one is x1, xk. And again, as I said at the beginning, when I write this, I mean all permutation of such functions. The second one is this. What is this? This is a sum of the xi's that are nested into each other. So there's 1, 1, 2, 1, 2, 3, and I grow up to the same monomial that I have here. Now, this is a Boolean function for the output. This is real valued. So when I put plus, you could have in reality every coefficient you want here. This I don't care. Now I'm in the real line valued setting. This is Boolean, and you can choose your coefficients. Okay, let's start with these two. So if k is finite, so think of k finite. K finite in D. In the back world, in the free algorithmic world, these, you know, they all have the same, you know, it doesn't matter. They're sparse and you can learn them efficiently in sample and time. But let's see what kernels can do. So remember, the game with kernels is you define a few feature maps and you choose them ahead of time using the knowledge that this is the class of function or this is the class of function. And now you check, you know, what's the sample complexity. And so with kernel, it turns out that this, here you pay by having a high degree function k here. As opposed to the backward, kernels are in bigger difficulty. You can see that if the function, if k was 1, you know, if the function is simply some xi, you don't know the I, then you can put a feature map that is the input itself, and you know, gradient descent with, you don't have to use a feature map, you directly pick up who's the coefficient that is being learned. If you have xi xj degree 2, this is completely uncorrelated with a single of these elements, but you can use, you know, a feature map that are all the pairs xi xj, and you will pick up the right one. But now you have already used d choose 2 features. And here I'm putting something on the rock, which is that there is a duality between number of samples and number of features in kernel learning. And so, you know, thinking of how many features you need is actually connected to how many samples. Okay, so I want to talk about, again, regular neural net, so I will go also a bit fast on this, but this is what happens.
This is like you pick the best possible kernel.
Yeah, if no matter what you do, you will never be able to beat d to the k. I can show you so the bound is like this.
The ground truth is just this function, or it's
The orbit of this function, so every degree k monomial.
one of those, you don't know which one.
Exactly. This you will require d to the k for kernels, no matter how you design the kernel. If you do this, do you think kernel can improve?
What is the question?
Can you beat d to the k when this is the class of function? So again, up to permutation, so the function could be x7 plus x7 x8 plus x7 x8 x6. Okay, any permutation you want, but it's it has to grow from degree 1, degree 2, and it has to be nested. So the answer is no. This structure is to a kernel, it's obvious because it still has to come up with, you want the loss, so maybe I should specify, I want the loss to be arbitrarily small, epsilon, to be arbitrarily small. So that means I will have to catch up that term. But the kernel, yeah, you set up the feature map once at the beginning, and then you look at the best guy in the span. You cannot really use this nested structure in a dynamic way with the kernel, because it's like a static thing. You choose your feature map and then you train. Okay, so now 2NN. This is, I guess I built up too much the expression. It's pretty obvious what the outcome will be, but 2NN is this class here that we define. So for these pure monomials, again you suffer like kernels. We will see that you cannot, and this is actually much less obvious to obtain than this one, but this will require also a bound that scale exponentially with k. This we'll have to discuss why, but the surprise is that here it will be back to D. It will not suffer from k. And what's the intuition? The intuition is that the neural net, it will start with this. It starts with the inputs which are exactly the degree 1 monomial. Okay, it applies this matrix, and then in this case, in 2NN, we directly go down after the nonlinearity. So it will easily pick up, for example, if it's x1 and the monomial, it will pretty easily pick up that x1 as an important contribution to the loss. But once it has x1, so here now I'm not going to say what the neural net does, but imagine that conceptually, if you factor out x1 of this equation, then what you see is 1 plus x2 plus x2, x3, etc. Okay, so if you take out the bias, then you're back to what you had before. So now you just have to learn a degree 1 monomial. And this is essentially, the neural net finds its own way to implement this, that to successively treat this as a sequence of linear functions. And so it will actually in only D, and of course here I'm skipping the constant, so I'm treating k as finite. This enters the complexity if now k grows, but when k is finite, there will be some constant that depends on k. But the scaling in D, which is what is large, is just linear. Okay, so I think I can state now this leap, at least with I said maybe the main element. And then I will tell you the general theorem and what we can prove and what we cannot prove. So this is this object definition. So again, f is a Boolean function. And let's call the leap of f, L of f, as the following. So decompose f in the Fourier basis and call S1 blah 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 as. And by the way, let me also stress again that this function is going to be k-sparse. So depends on k coordinate. I'll limit myself to this for now. And these are the set of Fourier coefficients that are non-zero. It doesn't have to be k, right? It could be that you can have as many as you want. They depend on k variables, but there could be L of them. L has to be finite, though. So the leap is this. Is the minimum over all permutation in the symmetric L. So I'm going to use into ordering of my L sets. Which order I start? Maybe I start with S2, then S3, then S1, etc. Of the following, the maximum over all j from 0 to L minus 1 of S pi j plus 1 set minus the union of j is equal to 0, or let's say I is equal to 0 up to j of the previous guy. Okay, so I'll parse it. So let's look at some example, maybe that's easier. So if your function was x1 plus x1, x2 plus x1, x2, x3 plus x1, x2, x3, x4, this is what we call the vanilla staircase. Here the sets are, the first set is 1, and then I'm going to use this permutation that you can read directly here. So 1, 1, 2, 1, 2, 3. And what you see is that the new set always increments the union of the previous set by only one element. So the leap of this function is 1. This would still be 1 if I did something like that here. If I do x2, x3, it's still 1 because 2, 3, you only have to add the coordinate 3 to what you have seen to increment. Now a bigger leap would be something like that. So x1 plus x1, x2, x3, x4, x4, x5, or yeah, let's do something like that. So here you take this guy with only degree 1, so you always start with the lowest degree. And if I start with degree 2, then it's already a leap of at least 2. Then here I would need to grow 3 guys. Here also 3 guys, so okay, maybe I say 7. So maybe I choose this, and then I choose the last one, which is a leap of 3, sorry. In this case, it's a leap of 3. Okay. So what is the result? So first I'll say, okay, first I'll say the claim, and then I'll tell you what we can prove, what we cannot. So the claim is this, is that 2 and n can learn with arbitrary small epsilon, delta is 1 over 10, if and only if, I have to explain a bit, I'll write it like that, so that if the sample is d minus 1. Okay. So this class of neural networks here, these 2 NNs, with SGD, we learn. And the epsilon shows up in the constant, also in the width of the neural net. But it will learn with the sample complexity, which is this. So this is both the sample complexity, because we use SGD, it's also the number of steps. Right? Because in SGD, each sample is 1 step. So the time complexity is going to be all d to the L. Because each step you multiply by d, which is the dimension of the gradient. So the surprising here, or the good news, is that we believe it's an if and only if. So it characterizes for the class of Boolean functions that are sparse, and for this type of regular neural net, the learning. Okay, so okay, how much time do I have? I'm not planning to do any proof, just to tell you I'll just tell you what we cannot prove. Okay, so 3 remarks. I hope it's. I'll do them quick. It's important to notice that there's really the hierarchy. So the conclusion is what? The conclusion is that these regular neural network, they require a hierarchy to learn. We cannot do like pack the last term directly. And it's also a directional hierarchy. For example, if so it needs hierarchy that's growing. If your function was the last monomial, you do x2 up to xk plus x3 up to, xd. If you know the staircase that goes downwards, that has a huge leap because you have to directly climb all the way up. And this you cannot learn in OD. So it's really, you have to start from linear functions and then successively build. So that's the first point. The second is, is that it beats kernels. So basically, this manages to beat the curse of dimensionality that kernels have, but it's still not the free world in the regular world because of this example. For example, the staircase that goes down. Now, what we can prove, it's actually to explain there are a few restrictions. So there are two cases. The first case is when the leap is 1. We use the theory of Montanari, Sangmei, and Tio, who is a co-author. Because the advantage is that when the leap is 1, you can hope to learn in OD, which means you can hope to learn in constant number of steps. And this allows us to approximate the dynamic of GD with this mean field dynamic. But even there's quite a few things to do. For the negative result, we use the mean field dynamic, and it's called the dimension-free mean field dynamic, so it's a specialization of it that exploits this sparsity. But for the positive part, we have to do a layer-wise training. And for a larger leap, we need quite a bit of artillery. So we have to use layer-wise training. We go to the inch loss. It simplifies the computation. We have to use a specific activation, which is a shifted value, so that's not too bad. We have to use a gradient descent with a specific learning rate. So none of this seems necessary, and the result seems to be true. We did experiment in a much broader sense, but that's quite a few restrictions. And very last picture, and I'm done, is that what you see is that the training, when you have leap k, is really following these plateaus like this, which means for some time you're stuck with d to, let's say, the first monomial is maybe cube, and then d squared, and d cube, and he doesn't know where to go, and he has to search the next direction, and once he finds it, he dives and improves. Voilà.
Right, thank you. So we have time for maybe a quick question.
How does it depend on K and L?
Yeah, so L, there's no dependence. It's on K, the dependence. The dependence on K is in two ways. First, in the number of hidden neurons that you need. In this model, this capital N will scale exponentially with K. Okay. So if you do depth 2, you have to pay exponentially in K here. And in fact, we have another paper that came out before this one, where we did deeper networks. And there we don't have a dependency which is exponential in K. It's polynomial in K. But now the depth is polynomial in K. So now the depth grows with the... I didn't mention this result first because the architecture is a bit less standard. It's a sparse, it's still regular, but it's a sparse neural network. But essentially, if you only do 2 layers, you have exponential in K here, but if you do depth K, then you have poly K.
All right, okay, thanks again.